We'll continue discussion on operational amplifier. We have so far used amplifiers which only use resistances, but now we'll introduce the concept of introducing a capacitor also, which means now the circuit will become frequency dependent. That opens many wide range of applications for op amps. We'll look at two main applications which are called integrators and differentiators. So in both cases, what we'll do is we'll use R will replace R's with impedances. So we'll see. It can be just resistance, can be capacitance, but in both cases, the important thing is that our output will be now a function of frequency. So if I would write it for the frequency application, I would now write my relationship as dependent on S minus Z2S and Z1S. Of course, if it is resistance, we just write resistance, but if it is a frequency dependent component like capacitor or inductor, then we use the value of S. And S is J omega, which is the actual physical frequency. So transmission magnitude and phase for the input signal of omega. There's an example in the book which just emphasizes the important concepts related to the example of using a capacitance and a resistance in the feedback loop. So what it does is it instead of using Z1 we use R1, and instead of Z2 then we are using a parallel circuit of R2 and the capacitance that is there. We can call it Y2. For all practical purposes, when we replace Z2 and Z1 in this relationship, we get a relation which has dependence on not just resistances, but the gain is also now dependent on capacitance. So this would become minus 1 over R1 plus R2 plus SC2 R1. And if we talk about DC, in that case S will become 0. We will revert back to the original closed loop gain of an amp with inverting input, which would be minus R2 over R1. So it's the same, everything is the same, but now we have added complexity that comes from introduction of a reactance in the circuit. Now for this relationship we can for these kind of circuits we can revert to table 1.2 from chapter 1, which gave us transfer function and a whole bunch of things that are important for these circuits. So if I remind you, the transfer function was T was equal to K over 1 plus S over omega naught. So we know many of those things now from that table, and they can be implemented here. So if I were to apply this into to find the DC gain of 40 dB like this example asks, so 40 dB translates to 100 volt by volt, and it's asking us to use an input resistance of 1 kilo ohm, so we'll have to use 100 kilo ohm for R2. And now for the cutoff frequency, we'll have to put 3 dB on left hand side, and that would mean 1 kilohertz would be on the left hand side, and that would translate into 1 times 1000 times 2 pi, which will be equal to 1 over C2 times R1 R2. So that's the straightaway way to find the what kind of capacitor would we need to achieve 1 kilohertz cutoff frequency, 1 kilohertz of 3 dB point. All right, so when we use capacitances and resistances, what we get is we get either integrator circuit or differentiator. So this left hand side is what's showing integrator circuit, what we have done is we have used a capacitor in the feedback and resistor is in the input. If we think of mathematical integration, we are basically integrating our input signal, which is voltage, over time. So it's a time variant signal, and we are integrating this over time. So if we start with time t is equal to 0 and we go up to some arbitrary time t, then we would have deposited on capacitor a charge equal to, which would go from 0 to t, I sub t dt, right? So now in this case we are calling it I1, so I1t, and the relationship for the accumulation of charge. If the initial voltage is denoted by Vc, then we can find out what is the voltage on the capacitor over time, and we use the basic fundamental relationship, which is uh, Q is equal to CV. And now of course current would mean time, so we'd be finding out, dividing by time to find how much charge is accumulated over certain time that is of our interest. So if I were to write the uh, voltage on the capacitor, that would be the initial voltage plus the charge divided by C accumulated over time, I1t dt, right? So that would be the voltage on the capacitor. Now, how much is the voltage seen on the outside, on the output? So then we have to revert back and do two things. One is this is this voltage that's shown up there, and it has to be reverted in signal. So what we're going to do is we'll simplify this, and what we get is we get output voltage V output, of course with respect to time, would be minus 1 over C R RC integrated from 0 to T VI T dt minus Vc. Now this is then the initial condition, and RC is the integrator time constant. Now circuit output voltage is now proportional to the time integral of input voltage. That's as simple as that. Now when we are using frequency domain, we can then use R's and Z's for these two, and in that our relationship, our gain would then translate into V naught from signal. The output versus input would become minus 1 over SCR, just like we saw before for a generic case. And it will be out of phase because of capacitance, and our phase would be 90 degrees here. Now, if we have to see how does it relate to the original analysis which we did for DC, if we replace S to 0, we'll see that it reverts back to the original relationship that we had, and we have seen that before. Now for frequencies, omega, which increases over time, how does the magnitude change? So we do use Bode plots. So Bode plots are where we can see the behavior or get the transfer function of a device. So we see that as W increases, the magnitude goes down, and this is the kind of behavior we get. And this plot shows us a few things, that it's a straight line of slope minus 6 dB plus per octave. So this is log, of course. This is voltage. This is also in dB. Voltage divided by voltage, output voltage divided by input voltage, magnitude. So this straight line is equal to minus 20 dB per decade or minus 6 dB per octave. And here we see that the cutoff frequency is or the integrator frequency is the inverse of the integrator time constant, and that is 1 over RC. So this is a low pass filter. So everything is passing below that cutoff frequency and nothing is going above that cutoff frequency. So, and this is almost similar to the transfer function as we saw before. If you look at this guy and you plug in, use a capacitor to be an open circuit, which would be for DC. In that case, that would mean there will be no negative feedback. There will be no negative feedback, and it will have infinite gain for DC, which would mean if C is not there, you get an open circuit, and there is infinite gain. Of course, it will be restricted by the saturation, which we saw L plus, L minus, this power supply voltage. So what we do is we add feedback resistance, so we can get DC gain when it's working at low frequency or zero frequency. So that DC gain, DC, this RF would then result into a gain for just DC. But this RF is something we have to be careful when we choose, because lower the RF, higher the corner frequency, which would be now 1 over CRF, and it would be more non-ideal in that case. Now, another thing that we do with RC is here we have switched the capacitor with resistance. Input is still VI with respect to T, and there is a virtual ground there. And that means that the VI is across the capacitor, because on the other side is zero virtual ground. Here it is virtual ground, so the whole voltage is supplied across this, and that's resulting into accumulation of charge, which is causing that current to flow on the other side, and this current is C dVi over dt, and this is passing through the resistor, so our output is minus CR dVi over dt. So hence, this is differentiating the input signal, and what you get on the output side is the frequency domain transfer function of the circuit, which can be found by using 1 over SC for Z1, as we discussed the generic case at the start, and Z2 would be just resistance, and that would result into the gain V out over V in to be minus SCR. And of course, it's J omega. When you plug in J omega, we can get to the transfer function magnitude, which is the omega CR. So Bode plot for this also is something which has similar change, but the octave base change is now in the opposite direction. Let me just say something about the phase also. Now this would be minus 90 in this case. Now what happens to the change of signal respect to time? So we know that this signal is increasing as omega is increasing. So omega is on log scale. This is also dB input or the gain, and this is then the cutoff frequency, or we would also call it the differentiator time constant. And now we can see this is a high pass filter. There is everything would go above that frequency and not below that. So if you think about it, we should see that the nature of a differentiated circuit would cause it to be a noise magnifier, which if it's because if there is a spike introduced at the output every time there is a sharp change in the input voltage, and that could be interference coming from somewhere, any signal that's picked up from adjacent signal sources. So this means that it has stability issues. So we generally avoid these, but it's usually necessary. If we use it, then we have to use a small value resistor in series with the capacitor. But that again takes it away from non-ideal differentiator. So far we have talked about ideal op-amp, and for the most part we use these relationships to define the op-amp finite gain and the closed loop. But in many applications, our ideal op-amp assumption just breaks away. So we'll look at some of those. The first one of those is these imperfection is what we call DC offset voltage. So if you think about it, this would be like there is an added uh, there is a problem with an op-amp. So even if you tie the two inputs together and ground them, we would still get a signal on the output. So despite zero differential signal, some finite voltage exists. We can bring the output back to the ideal value of zero by connecting a DC voltage source of known polarity. Like in this case, we are showing a VOS inside an op-amp. So that is something which is this VOS is adjusted to be equal magnitude of opposite polarity to the voltage that we need to offset. So there are unavoidable mismatches in the differential state inside an op-amp. We will not go into too much detail, but we just have to identify that the general purpose op-amps, they exhibit VOS in the range of 1 millivolt to 5 millivolt. It depends on temperature also, but so look at spec sheet when we are using an op-amp. What happens when you have these imperfections? So for example, this exercise talks about sketching transfer characteristic of an op-amp with these imperfections. So if you look at it, we have to apply and show the offset voltage in the transfer characteristics, and that results into shifting of the transfer characteristic to the left. We have very straightforward ways of finding the performance of VOS, the effect of VS on the performance of op-amps. What we do is we input voltage signal with short circuited, and the op-amp is replaced with the model that's shown in this figure. And we find that for both configurations we find what is the output DC voltage. We're using a relationship which is V naught equals VOS times 1 plus R2 over R1. So this output DC voltage can have a large magnitude. For example, if a non-inverting amplifier with the just a closed loop gain of 1000, so with 5 millivolt input offset would result into a DC output voltage of plus 5 or minus 5 volt instead of 0. Now, if when we apply an input DC signal or an AC signal, our output would be superimposed on this 5 volt DC, which is coming because of that the offset that we have applied. So obviously then we wouldn't be able to know what signal is belongs to the actual input signal and which does not. So sometimes some op amps have two additional terminals to where we can apply it. We can apply an outside we can connect an outside circuit to trim to zero the output DC voltage, which is because of offset. So there are different ways how it is done. So here are a couple of examples that are shown how it is done, and these are the some ways how it is done to take care of that offset voltage. So another solution to take care of that this imperfection is to use capacitor coupling the op amp. Now this would result into zero gain for DC, but your output would be equal to the signal output that's fed to the circuit. So in this case, the capacitor forms an STC, the transient single time constant circuit with R1, and this would be a high pass filter with omega that we can calculate from that capacitance. Another important thing that we see is input bias and offset currents. So the idea is that we can apply the input terminals with bias currents. We can apply bias currents to the input terminal, and that would be something where we would the total bias current would be addition of these two. So although an op amp has high input resistance, we apply these currents, and the difference is called the input offset current, and we get it from IOS equals IB1 minus IB2. The spec sheets give you the input bias current. It can be few nanoamps to hundreds of nanoamps, and what they do is they also take care of the imperfections that are associated with that. And on the if you look at an input bias circuit like this, so we think about what is the output voltage due to this IB that's supplied to the circuit, and we can see from this circuit that V naught or V output should be IB1 R2, right? Because that's the current going through and that's the voltage drop that it is seeing, and this is almost equal to IB itself. Now if we introduce another resistance in the non-inverting input, that can help, and what it does is it doesn't affect the signal, but if you look at the analysis, then output voltage is a function of the two currents as well as the voltage divider that's being formed because of R3. So if I were to write the whole voltage drop that's seen on the output, I would see it as the difference between these two currents, and this IB2 because of the path it takes, and whatever part comes through to the output signal. So now IB1 is almost equal to IB2 because of virtual ground. So we can give it one name, IB, and that simplifies our relationship, where we can now say V naught is equal to IB times R2. So now all we have to do is deal with the network of resistances. And V naught, or output, can be made zero by selecting specific resistances, which means that by choosing careful resistances, we can get rid of the signal at the output that would come because of these currents, the input bias current. So we would take non-ideality back. So for example, if we have to work on this, we can take R3 to be equal to R2 over 1 plus R2 over R1, and that can then cancel it out, and we would be left with zero voltage, and that would take care of our signal at the output coming because of the imperfections of op amp. So continuing on this idea that what can we do? Yeah, so this is showing that we can figure out what would be the resistances to take care of those signals. How would that affect on the offset voltage and offset current on inverting amp? So what is their effect on the actual circuit that we make? So let's consider the integrated circuit that we did before. So we short circuited the input signal source. Now, and we said that at time t is equal to 0, the voltage across the capacitor was 0. The output voltage with respect to time would be this guy now because of the offset voltage. So which means that the output voltage will linearly increase with time unless the capacitor or the op amp saturates. So that's not something we want. We don't want it to increase it without our signal at the input. And the same thing is for the current on the offset current gives the same problem. So if you think about offset current, it will flow through the capacitor and cause the output voltage to ramp linearly with the time again until the op amp saturates. So there's the we saw that before, where in integrator we added an RF to make the circuit behave for DC also. So that resistor provided a DC path when the capacitor was open circuit. So to keep the DC offset at the output small, we would use a low value of RF in that case. But lower the RF, the less ideal the integrated circuit becomes. So if you see, these are the competing issues when you are designing an op amp, and that's where we have to be carefully designing our circuit and components of our circuit that go with that. So the differential open loop gain A of an op amp to be not infinite. So it's infinite and it decreases its frequency. Now what this figure shows is the plot for the gain with typical numbers of a general op amp like popular 741 type. Now what we are seeing here is the gain is quite high at DC and low frequencies. It starts to fall off at a low frequency which is 10 hertz here, and we call this the break frequency or 3 dB point, right? So when it starts falling below 3 dB value. Now if we think about the STC circuits that we saw before, the gain of this circuit can be expressed as the gain, as we know, over 1 over S divided by the break frequency. What's happening here is as the frequency goes up, our gain ultimately reaches here, and that would be situation what we would write as A naught omega B over j omega, which is S. We could write this also j omega. And in this case, if we want to find the gain, that would be the value from the right hand side without the j part, and that would be A naught omega B over omega. So we see that as this reaches here, we reach 0 dB point. So 0 dB is unity gain. So what means is the op amps generally which follow this kind of border plot are have unity gain bandwidth. And for omega much larger than omega B, the gain simply becomes the frequency omega t divided by S, which is this point. So if this Ft is known, which is in this case is 10 megahertz, we can find the magnitude of the op amp gain at a given frequency F. So in actual practice, the spread of the value of Ft is much smaller than what is observed for open loop gain and breakout frequency, so break frequency. So we use Ft as a spec parameter which is given by the manufacturer in many cases. So let's take a look at example to see how frequency response changes with an amplifier with the given gain of plus 10 and minus 10. So what we do is we use this relationship which is given as equation 2.53 in the book, and we plug in the values here, and what we get for different gains, we get R2 over R1 values that has to be used to get that specific omega, and we get 3 dB point by this. So that tells us what is the break frequency for any given situation. Now this amplifier has a 3 dB frequency which is Ft divided by 2, and that's compared to the unity gain where it was just Ft. So this illustrates the trade-off between gain and bandwidth. For any given op amp, the lower the gain that's required, the wider the bandwidth that we can achieve. And this is what we would then use as gain bandwidth product, and that has to be equal to Ft of the op amp. So far we have looked at the small signal. But what happens when we have large signal applied on an op amp, especially when we are talking about the saturation, which is in between L plus and L minus. So there is limitation on the performance. It will be giving linear operation over limited range of output voltages, and that will be between L plus and L minus range, which is within 1 volt of the uh, outside voltage VEE and VCC. And here's the example that if these power supplies are plus minus 15 volt, our signal saturates at plus 13 and minus 13. So our rated output voltage is plus minus 13. And that's the case for 741 op amp, which has then maximum output current of 20 milliamps. And this is the range. So our design would then not require more than 20 milliamp, and that has to we have to play with the feedback and the load resistance to get to that value. Another imperfection is called slew rate. So it's a nonlinear distortion. It's specific maximum rate of change that's possible for the output of a real amplifier. So we would write it as slew rate equals dV output with respect to time. How fast can we change the signal that our output can follow that? So we may be going straight and have a kind of a abrupt change, but our signal cannot follow that kind of abrupt change. So we see there is a much slower or gradual change. So this is something different from bandwidth, and this is about how fast the output can follow the input. And it can cause nonlinear distortion to an input signal when its frequency and amplitude are such that the output voltage is required to change at a rate which is much, much more than the slew rate. So we need to know what is the slew rate so we don't uh, lose important information in our signal. Now, given the output limitations, we if this happens, we then call the output to be slew rate limited. And there are specific ways how we can calculate that. This output would be expected if the because of the finite op amp bandwidth, and we write it in a way V output or VI is equal to 1 over 1 plus S divided by omega t. So if you use R1 infinite and R2 0, like we did with closed loop gain, so our output would be then an exponential function of the input by 1 minus e to the power omega t times t. So this then shows the initial slope of this exponentially rising function is omega t times voltage. So as long as the voltage is sufficiently small, our exponential value stays below slew rate. So output can be considered to be following the input. Another imperfection is full power bandwidth. So slew rate causes nonlinear distortion. Now consider a unity gain follower circuit with Vt is Vi sine omega t, and the rate of change would be input respect to time omega and input average cos omega t. So maximum value would be omega vi and a cos function. So the maximum is at the zero crossing of input sine signal. Now, if the input is larger than slew rate, we get this situation where the theoretically the output should follow the cos signal, but what it does is as soon as it gets here, it starts falling. It's always lagging, and the large rate of change of the sine input zero crossing results into the op amp slewing. So data sheet gives us this function what we call FM, which is full power bandwidth, and that helps us design our circuit that we stay within the limitation and we don't get into distortion. So the output sinusoids of amplitude smaller than the output maximum will show slew rate distortion at frequencies higher than this FM value. So FM is then found that with slew rate divided by 2 pi V output max.